This chapter is almost impossible to cover online, so I will concentrate only on the problems. This is a diagram for a series or universal motors, which can run in DC or in AC. Notice that the same current flows through the field and also the armature windings. The stall current is the same as the starting current, which is also the same as the lock rotor current. Using the formula shown in the diagram, we can calculate that the current is 12 amps, which means that the motor has a high starting current and therefore lots of starting torque. When dealing with AC motors, we no longer say field and armature. Instead, we say stator and rotor. The speed of an AC motor is determined by the frequency of the line voltage and the number of poles in the stator windings. If the frequency of the AC voltage is 60 Hz and the stator has 6 poles in the windings, then the speed is 1,200 revolutions per minute. An AC induction motor has 2 windings in the stator. They're called the main winding and the start winding. There is no electrical connection between the stator and the rotor. The motion is caused purely by magnetism. In the main winding, we are given the current and the active power, and then we use the voltage to calculate the apparent power in volts amps. Because the main winding is purely inductive, we can expect a phase angle between the voltage and the current. Using the formula shown in the diagram, we can calculate that the current is lagging the voltage by 54 degrees. In the start winding, we are given the current and the active power. And once again, we calculate the apparent power, in this case 106.4 volts amps. The start winding contains a capacitor, so we can expect that the current will lead the voltage by a certain phase angle. Again, we use our formula and find a phase angle of 36 degrees, which means that the current in the start winding leads the voltage by 36 degrees. In conclusion, we find that the start current is leading by 36 degrees, but that the main current is lagging by 54 degrees, which means that the start current is leading the main winding by 90 degrees, and 90 degrees is ideal for starting the motor. Here is another induction motor. This time we are given the volts, the current, and the active power. We use the voltage and the current to find apparent power. This time we use active power and apparent power to find the cosine of the phase angle. The cosine of the phase angle is the power factor, in this case 0.8 or 80%. A power factor of 80% means that 80% of the power has been converted to useful mechanical power. Here is an induction motor with an active power of 460 watts. This is also the power into the motor. We have also measured the torque to be 2.4 Newton meters and the speed to be 1725 RPM. If the motor is in rotation, then we have mechanical power. Then we use our formula, and in this case we calculate that the mechanical power is 433.5 watts. In all motors there will be some loss, and in this case it's active power minus mechanical power. 26.5 watts is very low. The efficiency of a motor is indicated by the Greek letter eta. The efficiency is calculated by power out divided by power in, or mechanical power divided by active power times 100%. In this case, it's 94.2%. This is a very high efficiency.